In the last lesson, we learned all about non-dimensional groups called pi groups, and we found that you can basically take a bunch of variables, turn them into some dimensionless number, and that's called a pi group, and that all the different pi groups related to some problem are related through some functional form, where one pi group is some function of all the other ones. The question is, why was this important? Why do we need to know that? And in the context of the previous lesson, we're just trying to reduce the number of variables. So by having 5 or 6 variables, we can combine them down into 2 or 3 different pi groups. So we went from 5 or 6 variables into 2 or 3, which again helps. But there's another reason why we want to use these non-dimensional groups, and that's the point of today's lesson. So today's lesson is all about similarity. That's something that's used a lot in scale model analysis. So if I have something big, like a car or a blimp or a plane, you want to test that before you actually build it, because it's a lot cheaper to build a small one, test it to see what you need to fix, and then build another one, etc. Instead of building the whole big thing, having to test it, realize it doesn't work, and go back and have to build a whole new big one. So it saves yourself a lot of money to do scale model analysis. So when we do that, we generally take a small version of the same thing, but when we test it, we want to make sure that it's going to behave the same way that the real one will, and that is what similarity is. So there's two things we need to make sure happen. The first one is geometric similarity. So that's just making sure that the small model looks exactly the same as the big one. So same features, same shapes. If there's a little thing sticking out of the big one, you want it to stick out of the small one. Just basically want to look exactly the same, but on a smaller scale. And then the second one, the one that we're going to be focusing on in this lesson, is called dynamic similarity, and that's making sure that all my pi groups have the same values. And the reason for that is, remember, they're related through this function, and so if all the variables inside the function are given the same value, that's going to give me the same value out of the function. So that's what I want for dynamic similarity, and that's what I want to do to make sure that my little model test is going to replicate what's going to happen in the real world. So as an example of this, let's say you want to design a blimp, and so instead of actually building a full-scale blimp that is 5 meters in diameter, 30 meters long, you decide to build a 1/10 scale model, so only 0.5 meters in diameter, 6 meters long, because that's a lot cheaper. Not only is it cheaper to build, it's a lot cheaper to test. Generally, anything goes in the air, you're going to have to put in a wind tunnel. Diameter of 5 meters, there's not many wind tunnels in the world that even have a diameter of 5 meters, never mind being able to put a blimp in it. So that's going to be really expensive if you try to test that in a wind tunnel, if you even can, if it's even possible. Little guy, a lot easier, find a lot more wind tunnels, they're a lot cheaper also. So decide to go with that, make sure everything works out, and then if those tests end up going well, you'll build the real one. Real one, generally called a prototype when we deal with this analysis. So when you do the tests, I have my real blimp, the real prototype. I want to have 5 meter diameter, I want to have a 60 meter length, and I want this thing to fly at 10 meters per second. So in terms of my model, when I go and do the tests, this thing 1/10 scale, so the lengths and diameters are divided by 10. What should we use for the velocity to make sure we achieve that dynamic similarity I was talking about earlier? Remember, the way to figure this out is to make sure that all the important pi groups are going to have the same values. So generally the first thing you're going to have to do is figure out what are you testing, what are you trying to find, what variables are involved in your problem. When you do that, you go through the dimensional analysis we talked about in previous lessons, and then you find your pi group relationships. In general, one of them that's always going to show up as long as you have viscosity is the Reynolds number. So that's what I'm going to do in this situation. I want to make sure that the Reynolds number is the same in the model case as what I'm going to have in my prototype case. So the Reynolds number for my prototype, REP, the real situation, equals the Reynolds number for the model, 1/10 scale model. And so Reynolds number is density velocity times a length. So for my prototype, density of whatever air is going to be in, velocity, that'll be the 10 meters per second. Length, doesn't really matter if I use length or diameter, as long as I use the same one for both. And then viscosity, again, whatever the air viscosity is that I'm going to be flying my blimp in. And then when it comes to my model, that's why I need to figure out what my velocity is. So I know my length is going to be 1/10 of that length. I have a choice. Do I want to use the same fluid or a different fluid, different values of density and viscosity? I'm just going to go with the simple situation of using the same fluid. So if this fluid's the same, densities and viscosities are the same as well. So using the same fluid, I'm left with just Vp LP equals Vm Lm. So solving that for my velocity of my model, it's velocity of the prototype times length of the prototype over length of the model. 1/10 scale model, so this number is going to be a 10. So my model velocity is 10 times my prototype velocity. Prototype velocity is 10 meters per second. So my model velocity is actually 100 meters per second. Now you might have thought that 1/10 scale model should use 1/10 the velocity, or maybe you'd think that the velocity should be the same, but in fact I need 10 times the velocity for Reynolds number similarity to make sure that I have this dynamic similarity so that I'm testing the same conditions that the real blimp's going to fly in. Are these two pi groups, Reynolds number and coefficient of pressure, and then I know that one of them is a function of the other, so my coefficient of pressure is some function of the Reynolds number. So basically from that I can calculate my pressure based on this function of Reynolds number. Now when I did my model test, I want to make sure I had the same value of the Reynolds number, so I made my velocity 100 meters per second. Once my velocity is 100 meters per second, this RE value is the same no matter what. So I have an RE, doesn't matter if this is the model or the prototype value, it's going to give me the same number. So essentially what I have is that my two pressure coefficients are the same, so Cp for the prototype equals Cp for the model, or if I should use the equations, pressure for my prototype divided by 1/2 rho v squared is equal to same thing for the model. So from this now I can calculate if I measure a pressure on my model, I know the density, I know the velocity in the model, I know the density, and I know the velocity for my prototype, so I can back out the pressure on my prototype based on what I measured in the lab. So in this case, that reduces, if I rearrange this equation, the 1/2s go away. Again, I'm assuming I have the same fluid, so the densities go away as well. So the pressure on my prototype is the pressure that I measure on my model times Vp squared over Vm squared. But I know that for my prototype is 10, model's 100, so model's 100 times, or sorry, it's 10 times bigger. Squaring that, we get 100 on the bottom. So whatever I measure in the lab, if I want to know what the real value is going to be, you need to divide that by 100. So if I measure a pressure of 14 psi during the test, I know in real life what I'm going to get is a pressure of 0.14 psi. We can do the same thing for other parameters, such as the force, like a drag force. So I want to know how much drag I'm going to have on my blimp as it's flying. So again, same deal. I take all my parameters, in this case force replaces pressure, and so I still end up with two groups. In this case, Reynolds number and the coefficient of force, force over 1/2 rho v squared L squared. And then again, because I made sure that my velocity is 10 times bigger, I have the same Reynolds number. So I have the same Reynolds number and the same function. I get the same value for CF. So CF for the prototype is equal to CF for the model, or force on the prototype divided by 1/2 rho v squared L squared is force on the model divided by 1/2 rho v squared L squared. Using the same fluid again, take away my 1/2 and my density. I'm left with force on the actual prototype. It's going to be the force that I measure when I do those model tests, times Vp squared over Vm squared times Lp squared over Lm squared. Then again, I know that my model velocity has to be 10 times bigger, so I have a 1/10 squared from that guy. But then my length is a 1/10 scale model, so Lp over Lm is 10, so it's 10 squared for that guy. Those guys cancel out. I'm left with just Fm. So in this case, actually what happens is whatever drag force I measured on the model, Fm, is going to be the exact same drag force that I measure, or that's going to happen on the blimp itself. So if we measure, doing these tests, a drag force of 100 newtons, we'll have exactly 100 newtons on the real thing in the real world as well. So in the example we just saw, we need to test our model at 100 meters per second, but that itself may pose a few problems. So 100 meters per second, that's pretty fast. So a couple things could be a problem with that. For one thing, the wind tunnel might not be able to generate that amount of speed. The pumps might not be powerful enough, so you may have to go looking for a more expensive wind tunnel, which again is a bit of a problem. The main problem with that though is compressibility effects. So remember, we have to take into account all of the important parameters for our problem. We only took into account Reynolds number and coefficient of force or pressure. When we get up to higher speeds, compressibility becomes an issue, and so you should actually have the Mach number in there as well. And so we should not only have the same Reynolds number, but also have the same Mach number, and that's not going to be the case if I have different velocities. So that could be an issue as well. Luckily, in the previous case, 100 meters per second, you kind of just get away with it. That's kind of pretty borderline as to you can still ignore the Mach number. Anything above 100 meters per second, that's going to be important. So last case, we kind of got away with it. Anything higher than that, that would be a problem. One way we can fix this is to, instead of having a 1/10 scale model, maybe have a 1/5 scale model, because in that case, we wouldn't need 100 meters per second, only need 50. But again, in that case, my model's now twice as big, so now we need a bigger wind tunnel, and again, might be a more expensive wind tunnel. So one ways around these problems. So can you think of anything else we could do to maybe fix that? So the most common solution to this problem is to use a different fluid for the model tests. So instead of using air in the previous case, we could use a different fluid. For a lot of automobile testing, instead of putting the car in a wind tunnel, they'll put the little scale model car into a water tunnel. Water having different density and viscosity, you can get the same Reynolds number without having to have such huge velocities. So that's one very common solution. Another example of that is if you have a submarine going to operate in water. To do the model test, you have a 1/10 scale model like we had before, but instead of using water again, we could use ammonia at negative 17 degrees Celsius, because that has a kinematic viscosity that's roughly 30% that of water. What that does is, instead of needing 10 times velocity, we now only need 3 times higher velocity. So again, going back to the previous case, instead of being 100 meters per second, it would have only been 30, which is much more doable. So again, Reynolds number for my prototype, velocity length over kinematic viscosity equals that same thing for the model. So rearrange that for the model velocity. You have the prototype velocity, length, prototype over length of the model, kinematic viscosity of the model over kinematic viscosity of the prototype. Again, 1/10 scale model, so this guy ends up being 10 times bigger, but now using a different fluid, only 30% the kinematic viscosity, so that takes the 10 down to 3. Another way around this is sometimes you don't actually need the same Reynolds number to still have similarity, so I can get the actual same pressure coefficient even though I have a different Reynolds number. Now that doesn't happen all the time, but in certain situations it does. One of those is if you look at something called a Venturi meter, which is essentially a constricted pipe, so I have flow coming in, then the area of my pipe changes. So this is a graph of the pressure coefficient in the Venturi meter compared to Reynolds number. So you can see for small Reynolds numbers, 10 to the 0, 10 to the 1, pressure coefficients up 5, 6, somewhere in that range. But then as Reynolds number gets higher, up to 100, 1,000, 10,000, it gets closer and closer to 1. So anything above roughly 10 to the 3rd, it's pretty close to 1. So we just saw from the previous graph that the coefficient of pressure for the Venturi meter is roughly constant, approximately equal to 1. For really big Reynolds numbers, anything above roughly 1,000, CP value was roughly 1. Important thing about that is that it doesn't change. So it doesn't matter if I have a Reynolds number of 1,000 or 10,000 or 100,000, I have the same CP value. So in other words, I can take the two CP values for my prototype and my model and set them equal to each other, even if the Reynolds numbers aren't the same. But with one big important point is that both Reynolds numbers need to be above roughly 1,000 from that scenario, because that's where the two CP values were the same and independent of the Reynolds number. So this situation happens in a bunch of different scenarios, not just this one. The CP value may not be exactly equal to 1, but it could equal some other number. but that number is constant over a big number of Reynolds numbers. Usually the bigger Reynolds numbers, you have the same CP value. CP generally goes to a constant value. So in that case, you can compare them without having the same Reynolds number. So now time for an example of this. I have a 3-foot diameter constricted pipe. I have water flowing through there at 5 feet per second, water at 50 degrees Fahrenheit. So this is a situation that is kind of my real life scenario. I want to do some tests on this. I want to find what the pressure drop is, how much pressure do I need basically to get it through here in real life. The way I'm going to find that is using a 1/12 scale model. I'm going to use water slightly higher, 60 degrees Fahrenheit. And when I did that with 20 feet per second as the fluid velocity, I found a pressure drop of 1 psi during the test. And so I want to know in real life what kind of pressure drop does that correspond to. So first thing I can do in this case is find the Reynolds numbers for both scenarios, the prototype and the model. So standard Reynolds number equation, velocity times diameter over kinematic viscosity. I could use density and viscosity if I wanted to, but I'd rather only look up one number. So kinematic viscosity I can find in table B6 for water at different temperatures. So for my prototype, I have velocity of 5 feet per second, diameter of 3 feet, and then kinematic viscosity for water at that temperature, 1.41 10 to the negative 5 feet squared per second, again from table B6. Gives me a Reynolds number for my real pipe of 1.1 million. And then for my model case, same deal. I have the velocity that I was using, 20 feet per second. I have the diameter, a 1/12 scale model, so 3 divided by 12 in terms of the diameter for that. And then kinematic viscosity of water at that other temperature, 1.22 10 to the negative 5 feet squared per second. Gives me a Reynolds number for my model of 410,000. So again, these are not the same values, but they are both bigger than 1,000. So because they're both bigger than 1,000, I can still say that my CP values are the same, just like we saw from the graph. So I can still say that CP for my model equals CP for my prototype, and I can find my expected pressure drop in my real pipe through that. So just like we did for the blimp, CPP is CPM, or in other words, my pressure on my prototype divided by 1/2 rho v squared for the prototype numbers equals pressure that I found in the model divided by 1/2 rho v squared. Here, even though the water was at different temperatures, 10 degrees Fahrenheit, that does not significantly change the density. It's still 1.94 slugs per cubic feet in both scenarios. It did change the viscosity like we saw, but in terms of density, those basically cancel just like the 1/2 power. So the pressure on my prototype is the pressure that I found in the model times Vp squared over Vm squared. So the prototype velocity 5 feet per second, model velocity 20 feet per second, square both of those, multiply by 1 psi, gives me 0.0625 psi. So that's what I expect to have in my real pipe.